was just sending you some pictures.
Okay.
Okay, I sent.
Okay. See how fast the internet is. Must be a little slow tonight. There it is. Took about 15 seconds. I guess that's fairly typical. One on the left first.
Mm-hmm. Sure.
It's a JPEG file. They all been JPEG files?
I believe they have, yes.
Okay. All right, let's talk about the three general formulas for investing. Let's talk about them first. What's annual compounding? What's that formula?
Isn't that just what? I'm not sure. For annual?
Uh-huh.
Oh, isn't it just A equals P
That's the simplest one.
plus 1 is R times to the power of T? Yeah.
R is the rate, whatever the rate is. Okay. So if you're earning 5% per year annually compounded, then it's your initial amount times 1.05 to however many years. T is in years. T actually can be in anything, but typically with annual compounding, T is in years, almost always. Then you have less than annual. For instance, monthly. What's the general formula for that?
Monthly, it's A equals P and then parentheses 1 plus R over 12 to the power of 12T.
I'm going to put it like this, because this formula lets n be anything you want. So you use P for all of these. Mm-hmm. P being your starting principal.
Mm-hmm.
Notice the difference? This formula that I wrote covers any, if you're compounding quarterly, what is n?
The same as monthly, but instead of having 12, you just have 4 for the number.
So n is 4. If you're compounding quarterly, n is 4. If you're compounding monthly, n is 12. If you're compounding daily, what is n?
The same formula, just n is 365.
Right. N is however often you're compounding. N is the number of times per year that you're compounding. And then finally, there's continuous compounding, which is what kind of rules nature. What's that?
Continuous?
Mm-hmm.
Is that the PERT one?
Yeah, PERT.
Yeah.
With the RT and the exponent, and R is the rate. It's not 1 plus R. In other words, if we're dealing with a 5% rate, then R is 0.05. And on the continuous compounding, T can be in anything. It can be in hours, minutes, days. I mean, you got bacteria that double every 10 minutes. And whatever units T is in, R is in the same unit. In other words, if T is in days and you have a bacteria that's increasing by 10% per day, then R would be 0.1, T would be in days. So depending on the type question is which one of these you use. Now, are we doing 1, 2, 3?
Yeah.
Also 4, 5, 6 or not? Is that, oh, that's the second half. Okay.
Yeah.
Okay. So, you good with these? Can I erase them?
Mm-hmm.
All right. So, $100 invested at 4% compounded quarterly after a period of 2 years. What letter do you use on the left of the equal sign? A?
Yes.
So we got A equals, what's the general?
For this one,
Uh-huh.
1, and then it's parentheses 1 plus
Well, by the general, I mean without the specifics.
P times 1 plus R. Is it monthly? R divided by 12.
That's the general right there.
Okay.
And then you figure out what n is depending on the problem. In other words, this one's compounded quarterly, so n is 4. The next question is compounded monthly, so n is 12. Okay, now fill in everything. For problem number 1.
100, and then it's parentheses 1 plus, what's the rate? 0.04, and then divided by 4, the power of 4 times 2.
Perfect. And you get that number out of your calculator.
Mm-hmm.
All right?
So you got 108.
Yeah. I don't really care about the number. If you set it up right, we're not here to do arithmetic. Number 2, same general formula. Fill in its specifics.
1, or it's 50, and then in parentheses 1 plus 0.06 divided by 12, and then to the power of 12 times 3.
And this looks a little frightening, these huge exponents. Very first time I remember working with this, I said to myself, am I doing something wrong? Because that's an awfully large exponent.
Mm-hmm.
But notice that you're taking a very, very small number that's barely above 1. In other words, it's not even 1.06, it's closer to 1.005. And when you take numbers that are really, really close to 1 and you take them to gigantic exponents, they don't get that big. I don't know how big that number is going to be, but you'd be surprised. But don't be shocked by those large exponents. They are correct. And again, you get that out of your calculator.
Mm-hmm.
Okay, what's this going to be?
For 3,
Uh-huh.
500, in parentheses 1 plus 0.08 over 4 to the power of 4 times 2.5.
Okay, go to the next page. Bound to start getting harder here. You should have questions about how long does it take for $200 to turn into $600, things like that.
Mm-hmm.
No, number 4 isn't going to be it. Tell me what 4 is going to be.
300 parentheses.
One moment.
Okay. Oh, you get the fat one.
I have to take a screenshot before I can write on it in my normal pen. So A equals what?
300, and then parentheses 1 plus 0.12 over 12 to the power of how many years? 1.5 times 12.
Okay. Maybe they're not going to give us a hard one. Nope. Well, 5's getting a little different at least. What's 5 going to be?
600 times, or 600 in parentheses, 1 plus 0.05 over 365 to the power of 365 times 3.
Think. Again, that giant exponent would normally scare me away, and I would say, can't be that big of an exponent. But it is. Notice how small that number is going to be. So we're even closer to 1. Wow. Why did they even ask about 6?
I don't know. It's just the same thing, but with 700 instead of 600.
Yeah. I mean, what's the deal?
-6.
That is it for the problems they're asking you about this stuff?
I've got some more. I just sent you a picture.
Why don't you send me more? Because we haven't done any of the hard ones. The hard ones
the next one
would be where they don't give you the rate, but they tell you that it grows by some amount after a certain amount of years, and then they give you another question that makes you, well, what would it be in 15 years? So there's certainly some harder questions that you can get in this subject. One on the left first. Does it matter?
Sure.
You can't tell. There's also problems like half-life problems that can be quite challenging. Well, at least we have continuous compounding here. Whoop. Ink on that background doesn't work. Fill it in.
The general or just for this one?
What's the general?
P times e to the power of RT.
Okay. The specific?
10 times e to the power of 0.11 times 2.
Yeah. When you're doing continuous compounding, you really should have said per year. Right there. Because it isn't always per year. When you're dealing with bacterial growth, it might be 11% per day, compounded continuously. Or if they said 2 years, you'd have to turn that into 730 days. So the rates have to match with the units of t. You want to give me an answer on that? Do you have your calculator in front of you?
Yeah, I do.
Let's come up with an answer just so we can talk about whether it's a reasonable answer or not. In other words, you want to be able to make an assessment that this is a correct ballpark answer.
I got 12.46.
Okay. Now, if you took $10 and put it into a bank and compounded it at 11% annually, you'd have $11 profit at the, you'd have $1.10 profit. So at the end of 1 year, you'd have $11.10. And then you're going to get slightly more the next year, maybe $1.20. So at the end of that, you'd have $12.30. So we're definitely in ballpark. Continuous is not that different from the others over short time periods.
Mm-hmm.
If you're looking over a 50-year time period, well then continuous is a ton better than annual. And of course, the smaller the time frame, the better. In other words, quarterly is better than annual, monthly is better than quarterly, daily is better than monthly.
Mm-hmm.
And in fact, just for your info, you might find this interesting. If I take that formula, which is compounded more often than, or that's where n is the number of times per year it's compounded, and I let n approach infinity, that's what continuous compounding is. Is when n is infinity. In other words, when you are compounding continuously, that would be n of infinity. Well, guess what happens to that? As n goes to infinity, it turns into e to the RT. Based on the definition of e. This whole concept right there is all about e. The definition of e is the limit of 1 plus 1 over x to the x power as x goes to infinity. That is the official definition of the letter e. Right there. And that's how that, as n goes to infinity, how that turns into e to the RT. But it's kind of cool when you look at it like that. And it also shows you the significance of the number e. There's a reason e is the second most important number in all of math after pi. And it's because almost everything in nature follows that. Continuous growth or continuous decay. If you have uranium decaying, it decays continuously. There's no such thing as annual compounding in nature. The only reason we even have a formula for annual compounding is it was a creation of banks that wanted to pay you interest on your money. They didn't want to pay it continuous. They wanted to pay it at a little more favorable rate to the bank. Let's see. I gotta go back and get this page here. Well, these aren't even any fun.
That one's just the same thing, but it's got 40.
Right. Let me make one up for you, just so we can say we did a more difficult one. I don't know. Do you have any more after 10?
Yeah, I just sent you some. And these ones are the ones where you work backwards.
Okay. Let's look at some of those. Since we have a limited amount of time here, we only have like 10 minutes. Let's look at some of the harder ones. You don't need practice on the easy ones that you know how to do already. I mean, that's not where you need my help. That is somebody who just scheduled 3 appointments. Right here on my end. Okay, good. We have to use logs to solve these. So, the best way to start all of these out is with the general formula and then fill in what you know and solve it. So, let's do number 1. You're trying to get $100 after 2 years at 6% compounded monthly. We got monthly, daily, quarterly, continuous. So let's do the monthly one up here. prefer using that as my general formula. So tell me what I should write to start number 11.
You do 100 equals P, and then parentheses 1 plus 0.06 divided by 12 to the power of 2 times 12.
Good. In other words, this was more difficult because the rate was compounded monthly, and yet T was in years. So you got to make sure those units match. And that's why that exponent is 24. No, that's just T times N. I take all that back. Okay. That's actually an annual rate, which isn't clear from the question at all. This thing is not increasing by 6% per month. It's increasing annually at 6%, but compounded monthly. There's a difference. There's a big difference. Bacteria might grow at 6% per month, or other things, who knows. But, okay, so you don't have to use logs to solve. All you got to do is come up with this number right there in your calculator, divide both sides by that number. What'd you get for an answer?
We'll put that in.
Let's just, again, make sure you're in the ballpark.
For that number, times P, or just the answer needed?
Take 100 and divide it by that number.
Okay, I got 88.7.
What is it?
I got 88.7.
Okay, and that makes sense. 6% is not a great year. If you put $100 in a bank at 6, it would only grow 6% interest, $6 in interest in 1 year. So if you stuck 88 for 2 years, makes sense that it would grow to 100. Again, the difference between compounding monthly and compounding quarterly or annual is small, just like the difference between each of them and continuous, unless it's over a very long period of time. Now, let's see if we can find something. These are all exactly the same also. 21 is different. Tell me what 21 says.
Find the effective rate of interest for 5 1/4% compounded quarterly.
That's all it says?
Yeah.
Not sure what it means.
Me neither.
Find the effective rate of interest. Well, we're going to get is that 5 1/4?
5 1/4%, yeah.
Compounded what? Quarterly?
Yeah.
Okay, so I suppose the way we can do this problem wow, what do they mean by the effective rate of interest? Must be something a little higher than 0.0525. And I would say that the effective rate of interest is what makes that equal to 1 plus that effective rate of interest times T. In other words, if they mean what rate compounded annually would you need to give you the same amount as compounded quarterly, or then I think we'd solve it like this. And you would have to use logs. Have you had any of these problems where you have to use logs to solve them?
I don't think so. No.
I'm not sure this is the one to demonstrate it. This is kind of a weird problem. We would have to use logs. In 5 minutes, let me just make one up for you real quick.
Okay.
How long would it take $100 to grow to $500 at 6% interest continuous compounding? So here's the general. Whoops. So my question was, how long would it take $100 to turn into $500 at 6%? So you have to solve for t. The difference in this kind of a problem is we're not solving it algebraically anymore. When your variable is in the exponent, you got to use logs to solve it. What's the first step for solving this?
I'm not sure.
Divide both sides by 100. In other words, before we can use logs, we got to get that isolated. So
Yeah, that's true.
I got to get this. Now, if I take the natural log of both sides, I can then use the rules of logs to bring that 0.06t down in front on the algebra line.
And then would you divide the natural log of 5 by that?
Well, the natural log of e is 1.
Or by 0.06?
Well, the natural log of e is 1, so I can cross that out. So all I got to do is divide by 0.06 to figure out t. And that's what t would be equal to. If you get that number on your calculator, once you get it on your calculator, and I'm going to make a wild guess, how long would it take to increase your money by a factor of 5? You'd have to double it twice. I'm going to guess 15 to 20 years. Closer to 20 years. What is it?
I got 26.8.
26.8 years? A long time, but still 5 times on your money is pretty good.
Mm-hmm.
Tells you the secret to investing is holding on to it for a long period of time, letting t be big, because t is in that exponent. So when you let t grow, it really causes your principal to grow.
Mm-hmm.
All right, Sam, I will let you go, and have a good week. Talk to you next time.
Mm-hmm.
Bye-bye.